Okay, let's continue. So far in this course, we looked at ADCs at a system level. We kind of understood how to characterize its performance, blah blah blah. Then we started to look at the circuit level implementation. We began with the sampling network, and the first circuit we looked was this simple track and hold. Then we saw when we implement this switch using a MOSFET, we have a whole bunch of non-idealities. And in particular, we saw when we turn off the switch, we can have signal dependent charge injection that will result in non-linearity. And bottom plate sampling was one technique that can almost completely eliminate this. And then to process the sampled voltage, we did a whole bunch of things that gave rise to the switch capacitor amplifier. But then we saw in all these switch capacitor amplifiers or circuits, we were using an op-amp. So we started to see what all things can go wrong in the op-amp, the offset, flicker noise, finite DC gain, blah blah blah. We saw techniques to counter them. And in the last class, we came to the final realization that on chip we don't have an op-amp, that is a voltage controlled voltage source. Rather, we have an OTA, which is a voltage controlled current source. So the circuit looks like this. Just the op-amp replaced by the OTA. And in the last class, we saw one major difference is, although the OTA can be designed to have an intrinsic gain of infinity across frequencies, the moment you put it in this circuit, all these extra capacitors will load the OTA, which means the voltage gain from this node to the output will not be infinity across frequencies. In fact, at high frequencies, this gain drops to 0. The consequence is that whenever we transition to the second clock phase, the OTA will not be able to respond instantaneously and push the output voltage to the final value. And in fact, we've calculated what happens to the voltages just after we come to this clock phase. I don't know if I have it here. Yeah, we calculated here or here. Yeah, we saw that the virtual ground here, the virtual ground voltage in fact jumps up to minus K1 times some Vin, and only in steady state it goes to 0. Okay. So that is the thing. So we have to ensure that the time constant we have is much smaller than the time available for you to settle. And in this business, we didn't consider the effect of the switch on resistance. And the usual deal is to keep the on resistance to be smaller than 1 by G, right? And we also looked at what happens if there is noise, thermal noise. And as we saw, thermal noise is something fundamental. You just learn how to calculate how much noise will be in your circuit and size and design the component values accordingly so that the noise power is within the required value, right? Now, one fine point in this. So remember that when I'm showing this inverting, non-inverting terminals, finally it will all be connected to a gate of a transistor like this. So which means here I've told that I'm connecting this to ground. So which means if I connect it to ground, do you think this will be functional? No. So what should I connect this to actually? I mean, remember when I'm drawing it as ground, it is not the hard ground, it is small signal ground. So this is just a small signal ground. In the overall circuit, you connect it to an appropriate bias voltage, and you would have learned how to find ranges of voltages for which transistors remain in saturation. So you can apply a voltage in any of that range. But in practice, if the supply rails are from 0 to VDD, a common choice is to choose a common mode voltage VCM to be at half the supply so that we can have symmetrical swings both on the positive and the negative side. So we basically connect it to VCM. And even the input, as you know, you apply over a bias voltage like this, small signal plus the actual common mode. So if I do that, just now we saw that here or here or here. So when we transition to this phase phi 2, the virtual ground voltage jumps to minus K1 times the voltage sampled across the capacitor. So here again, if I do that, the voltage sampled across the capacitor is VCM plus Vi. So here if I look at this voltage Vx, looks like that will jump to minus K1 times Vcm plus Vi. So do you think then the transistor connected to this will be functional? The voltage here jumps to some negative voltage. It's connected to an NMOS like this. It will not be functional. And that's happening because you ideally want the OTA to respond only to the small signal Vi. But here it is responding also to the DC bias, which means you should not be sampling the entire signal across the capacitor. You should be sampling only the small signal. So what change I should do here so that I sample only Vi across the capacitor? Yeah, instead of sampling it with respect to ground, I sample it with respect to the same common mode voltage. So now the capacitor is charged only to the required small signal Vi. So now what will this voltage jump to? I mean minus K1 times Vi. This is okay, but still not great, right? I mean, let me make it here. This is okay, but still not great because this can still go negative. So ideally what we should do, this is the small signal. On top of it, common mode or bias should be added. Only then this will be functional. Clear? So as of now I have sampled Vi across it, and in the clock phase phi 2 I have connected it like this. I see that this jumps to just minus K1 Vi. Clear? Now I want to make sure this voltage is DC shifted by a bias voltage Vcm. What change I can make here? Huh? Yeah. If this one, if I increase, I mean now right now it is 0, so this is at some Vx. If I increase it to Vcm, it's a linear circuit, everything will scale. So finally that's what we will do. We will connect this also to Vcm. Now this will jump to this and things will be fine. Clear?
Initially when we do minus K1 into Vcm minus Vi.
No, the point is this voltage will jump to minus K1 times the voltage sampled across the capacitor, right? So that's why when this was at ground, this jumped to minus K1 times the voltage across the capacitor, which is Vi. Okay? But minus K1 Vi is also not great because that can still be negative. It should be coupled with a DC bias. So you basically boost the. So bottom line, I mean, whenever we drew small signal grounds, remember they're all small signal grounds. In the actual circuit, you go and connect it to an appropriate bias voltage that in principle can be anything so that the transistor remains in saturation. You would have learnt in other courses the ranges of voltages, but a common choice is to keep it this. Fine. So by the same token, even this you can put it to Vcm so that it's all. So this is something you have to keep in mind when you are actually wiring the circuit. Now again in practice, we don't have a single-ended implementation. We have a differential implementation. So whatever I have in one side, I have for the other side. That is, the input is applied like this, Vcm plus some positive input, Vcm minus the negative input. I mean the same thing, I have copy pasted it on either sides. The op amp is taking difference between the two inputs, providing it as a differential output. Don't have to worry how this is implemented, but as of now, this is how it is done in practice. And in the last class, we computed the noise for a single-ended circuit. Let us say that is some V out squared we calculated as some N naught. If for a single-ended circuit, that is for one half of the circuit, this was the noise power. I am having 2 times of this circuit here. What do you think will be the noise power in the differential case? I mean, loosely speaking, it should double because I have twice the number of switches, twice the number of noise sources. Everything doubles, and all the noise sources are uncorrelated, so it just becomes 2. So if someone gives you this kind of a big looking differential circuit, you first take only one half of it. So basically cut this into half. That basically comes down to this. Then you calculate the noise for this one and then multiply it by a factor of 2. As simple as that. Yes. Okay, there are a lot of advantages with differential signaling. You learn it in, you would have learned in other courses. So right now I'm not wanting. We can discuss at the end. Turns out on chip, the preferred way of applying signals is differential. Cool. So now you guys know how to sample a signal, and any non-idealities that come in path of you know how to tackle them. And we also saw how to take this sample signal, do any kind of processing you want, you can amplify it, you can do any kind of filtering. So we are experts in sampling and processing. So first part of the job is done. After sampling, what is the second job I have to do? I have to quantize. And quantization, as you know, is typically a process where you take the input signal, compare with some reference voltage, and see if it's greater than 0 or less than 0, right? A simplistic quantizer is one where I give an input Vi and see if the input is greater than 0 or less than 0, right? If it is greater than 0, I want to output VDD. If it's less than 0, I want to output 0. And mind you, again, the input will be applied over a bias. VCM plus a positive, VCM plus a negative input. So all I need is a comparator like this. If the input is positive, I have to increase the output so that it reaches VDD. If the input is negative, I should reduce the output so much that it goes to 0. Now from your understanding, what is one simple circuit I can use to achieve this operation? I have an amplifier. If I have an amplifier with a large enough gain, this will do. Clear? So if I have an amplifier with a large enough gain, if I apply a small signal Vi, you guys know it gets amplified a lot, and if the gain is large, this will saturate one of the rays. And what is the simplest amplifier that takes in one input and gives you one output? Common source, I'm sure everyone has learned, right? So even people who are taking 610 now would have seen this common source. And simplest common source is this. Put a resistor here and then have a common source amplifier like this. Simplest circuit. And what is the gain of this? Magnitude of the gain? Gm times R. Fine. This much everyone knows, I hope. So this is good, but in practice we do a modification. So what you can do is, see, remember I am going to have one clock period. So for one half of the time I am going to sample. In the second half of the time is where I am going to do the comparison. So this fellow need not be active in this clock phase. It only is required in this. So I can basically turn it off in the other clock phase. So what we can do is we can put a switch here. Okay. And let us say it is needed to be active only in clock phase 5C. So I'll just clock it so that I can turn it on and off as I need. And this is a switch connected to ground. How will you realize this? NMOS. So time to replace all ideal switches now. So this is an NMOS now. So I'll apply the same VCM plus Vi and you get the output here, right? Cool. Now in practice, again as we just saw, things are differential. So what you need in practice is this. I need to take in two inputs, VCM plus a positive input by 2, VCM minus the input by 2. So I have one circuit that works for positive. I need to also make another circuit that takes in the negative input. So simple thing, I'll do a copy paste. Actually push it here somewhere. I'll have another circuit like this. Oops. That is taking the negative side. Fine. And that will also be clocked like this. So I have two switches here. I can basically share the two. So that basically gives rise to this. I mean, what I'm saying is I also will have a switch like this. So I can share the two switches to a single switch and do something like this. Let me draw it neatly. So the inputs will be, I'll say, okay, I'll write it clearly, VCM plus positive input, VCM minus is and I define the output like this, right? Cool. So this is a nice simple circuit that will work. Let me erase this. So now let me ask this question now. I know the gain here is GM times R. So let us say this is when the comparator is made active. I apply an input VID and let's say that's greater than 0. So let us say the output is 0 here. When I apply the input and activate the comparator, ideally the output, if the gain is GMR, input is VID, what will be the output? GMR times VID. So ideally I expect that this jumps up to this. This is what I expect ideally from this circuit. But do you think it will jump instantly or what will happen in practice? Why? Remember, in life, you will have parasitic insects. Similarly, on chip, we have parasitic capacitors. So there will be always a parasitic capacitor from every node to ground. So which means now the capacitor voltage cannot change instantly, because if it were to change instantly, impulsive currents needs to be provided. Here there is no way for that. So how will it change? How will it change? It will basically do this. Right? So essentially it's going to take forever to reach. Okay. So can you tell me what is the closed form expression for Vout then? If it's exponentially rising like this, GMR into VID, that is the final value, 1 minus e power minus, fine. That's how it's going to change. And of course, as you see, this is going to take a long time. The comparator is going to respond slow. So basically here, the capacitor is having a memory. It is remembering its past. So it is thinking, earlier my voltage was small. So it's taking forever to respond. So that is one life lesson you can learn from comparator. Something didn't go well in your life, just don't keep thinking about it, thinking it didn't go well, because that will just make your progress slow. Cool. But anyways, so here what is time constant tau? If I call this R and Cp, R times Cp, okay. So ideally, how do you want this tau to be? You want to be small or large? You want to be small. Ideally, you want it to be 0 so that you can get instantaneous jump. If you want to reduce tau, remember parasitic capacitor is not under your control. Again, this will also include the capacitance of the next stage that is loading this. So what is the only control I have to reduce tau? If I reduce R, what else will happen? Gain decreases, right? So ideally you want to reduce this guy, but I don't want to have a small value for R, okay? Because that is going to compromise my gain. So one thing is clear, that I cannot touch the magnitude of tau because I won't have a large value of R. If I can't touch the magnitude of tau, what else I can change? For a number besides magnitude, what else is there? Phase. It's a real number. So what values of phase? Huh? Yeah, he's saying phase. Phase is 0 to 2 pi. Is there any value, any value of phase in this range that makes a number real? Huh? 0 is okay. Is there any other phase? Pi, what will it do? Pi? It makes it negative. So what we are essentially thinking is this is the tau axis. So let's say this is 0. So right now we are here somewhere. A large tau that is needed because I want to have a large r. Now this is causing issue. So hypothetically speaking, let's say we move here. Fine. I mean, doesn't sound very practical, but let's see. Thought experiment. Stay with me. If I have negative tau, seems okay. So let's see what happens if you have negative tau quickly. So I am having tau as less than 0. So capacitance is positive, that is a parasitic capacitance. Now it is a resistance that we are going and putting. So if at all this tau can be negative, what can be negative? I mean, again, let's see how we'll do this. So if r becomes minus r, how will this expression change? I mean, r becomes minus r, so this is minus gm r did plus t by tau. So this is gm r did e power plus t by tau. So now you see you have a positively growing exponential. If I try to sketch this, it will just instantly do this. It's an exponential growth. So it will just do this, and once it hits the supply rail, it will saturate. Clear? Sorry? This much is okay? Yeah, I'm just trying to plot this roughly here. The sense this has an exponential growth. So what will happen is it will kind of grow exponentially. So the point is, if you want to mimic this sudden jump, exponentially growing curve is the best thing you can have. Fine. So looks like this will be much faster. But of course that begs the question, how can I get negative R? It's not like you can go to a shop and say I want minus 10 kilo ohm resistor, you give me. Obviously it is not physically present. So we have to put some makeup and make it look like it's a negative resistance. Okay. Till this point it's clear. So let's see how we can get a negative resistance. Same thing, right? Whatever you put, it's not about the impedance being large. If you have a large impedance, that also means the time constant is going to be large. Right? Time constant being large will reduce the speed. Right? So first of all, let's understand what does negative resistance even mean. Okay? So let us say I have somehow discovered a negative resistor. Now we are trying to characterize it. So try to plot the IV relation like this. If you apply a test voltage, what is the current drawn in this direction? Minus Vt by R. So what is the current in the opposite direction? So that's what a negative resistor is. If you apply a voltage, it should pump in a current. That's all. So that means, in principle, let us say I have an ideal current source of value Vt by R. This should do it. But of course, I can't have a constant current, because if this voltage changes, I mean, things will not work. So you cannot have a constant current source. You need to have a current source whose value changes with the voltage. So what kind of current source it is? Voltage controlled current source. So now let's draw a voltage controlled current source. So yeah, let me draw it here. All I need is a voltage controlled current source like this. Let us say this is the controlling voltage Vc. Let us say this is some Vc by R. And here is where I apply the test voltage. Clear? Now I want this current to be equal to what? I mean, to get a negative resistance, what should this current be equal to? Vt by R. So what should Vc be equal to? So what should I do? This is Vc. I want this to be equal to Vt. What should I do? I go and connect Vc to 1. So that's still hypothetical. So do you know any voltage controlled current source? A transistor is a voltage controlled current source in small signal. So let's draw and see. So if I draw the incremental equivalent of an MOS transistor, so it's going to look like this. This is the gate, this is the drain, this is the source. If I call it, say, some VC, the current flowing down is GM times VC, okay, and I want to apply a test voltage here. So what is the difference between this and this? Current direction. So here I cannot simply go and connect it, right? Then I will be drawing out current. But if I were to pump in current like before, what should this voltage be connected to? If I connect it to, if I connect it to VT, I will be drawing current in this direction. If I connect somehow with this to minus VT, here okay. Fine. If I connect this to minus VT, then the looking in resistance is what? Minus 1 by GM. If I connect it to minus VT, the current drawn is minus GM times VT. Apply a voltage V, current is minus GM times V. Ohms told you long time back, distance is minus 1 by GM. So which means let's try to see what we can do here. So I'll try to replace this resistor with a negative resistance. So I have to connect a MOS transistor here, okay. So what kind of transistor I'll use? PMOS. I'll use a PMOS like this. I'm using PMOS here, remember, because source has to be incrementally ground. If I use an NMOS, that won't be the case. Fine. If I use an NMOS, the source will come here, it will get connected here, that won't get incremental ground. Okay. I connect PMOS. So let us say I go and do this. Hold on, let me align this. It's okay. So this is the node, drain. At the drain, if I apply a test voltage, I want to have a negative resistance. So here I see that the gate must be connected to negative of the drain voltage. This is the gate, it's at minus VT, connected to negative of the drain voltage. So here is the drain voltage. I have to connect this gate to negative of this voltage. So is there a node here that gives negative of this voltage? Remember, this branch is processing positive input, this is processing negative input. So voltages here, if it's plus, it will be minus. So what I have to do, take this gate, and what should I connect it to? I connect it to the drain of this. So essentially, if I logic clear? Okay. This point is okay, right? So we are trying to replace this VCCS with a transistor. So we are choosing a PMOS because source has to be incrementally grounded and source is at VDD. Now to get this negative resistance, if the drain is at a potential VT, gate must be connected to negative of the drain. Fine? Okay. So which means in one half I have done this, what should I do in the other half? I should do the same, it should be same, only then it is symmetric. So I will draw another PMOS, do a cross coupling here. It's clear? So let me copy paste this. So now we have come up with some circuit following some line of thought. It's time to actually go and see if it works. So let's try to briefly look at how the circuit functions. So let me assume the differential input is greater than 0. Okay. Yeah, and always remember there is parasitic capacitors. And let us say this is the time instant at which I have activated the comparator. So here let us say when the comparator was not active, both the outputs were equal, let us say. Now I have activated the comparator. So I am applying inputs here. The transistor will take the input, convert it to a current. So I will have currents flowing in both branches. Which of the currents will be greater? I1? Fine. So I am drawing currents out of this capacitor. What will happen to these voltages X and Y? They will drop. And which will drop faster? X will drop faster because we are drawing a larger current. So it will do something like this. And Y will do something like this. Okay. Now X is dropping faster. If Vx reduces, maybe I can write it here, Vx is reducing. So gate voltage of this P MOSFET reduces. What can you say about the current IP2 here? The gate voltage drops, current will increase. Fine. If the current here increases, I am pushing in more and more current into this node. What can you say about the voltage at that node? That will increase. Clear? So this voltage is increasing now. Let me mark it. So if this voltage is increasing, the gate voltage of this P MOSFET is increasing. What can you say about the current in this P MOSFET? Current reduces. If this current is reducing, I am essentially pumping in lesser and lesser current into this node, but I am drawing more and more current out of that node. What happens to Vx? That reduces further. Okay. So when I do this, IP1 reduces, so which means Vx reduces further. So this will keep happening in a loop, and eventually, yeah. So let us say Vy will start to increase and reach VDD, and Vx will reduce and go to 0. Okay. And here is where you get the e power plus t by tau behavior, exponentially rising. So now we saw that when Vx was initially reducing, a chain of sequence was triggered that further resulted in Vx reducing further. So what kind of loop is this? It's a positive feedback. I did some change, the loop is enabling the change. So this is a positive feedback loop. And this kind of exponential growth is what we call as regeneration. And one classic way of getting this regeneration is to use positive feedback. Clear? So yeah, I mean, see, earlier when I didn't have this loop, the capacitor here was having remembering its past. So it was thinking my voltage was low. It was taking forever. But here also, the capacitor is still remembering its past. But it is remembering its past and understanding that the voltage was low. But then a corrective action is imposed, and then you saw it works. So second life lesson, comparator is teaching you something didn't go well. No point in just simply thinking about it. You think about it and do some corrective action, then you will see an exponential growth. Cool. It's fine. Now this circuit is nice, but one minor thing needs to be done before we actually can deploy it in practice, and that I'll explain now. Now let us say the comparator here has made the decision VDD 0, right? So this is Vy, this is Vx.
initially X and Y were at some certain voltage.
Yeah, we assume they are equal. Let's not, we'll come to that later.
And then how we will what is this?
We'll come to that, we'll come to that. I'm coming to that, okay?
Just to clarify, if we're using this as a differential amplifier, the PMOS will directly be connected to the VDD and instead of IC, it will be connecting it to character.
I mean, this will be connected to VDD, no, right?
Like
Some bias voltage, yeah, correct.
And IC will be connected to a character.
Yeah. So let us say here the comparator has made a decision. So I am continuing this time axis here, okay? So let us say after this incident happened, so dy is at VDD, dx is at 0, okay? This is y and x. And let us say I have the next clock cycle happening. And in the next clock cycle, let us say the differential input is less than 0. If the input is less than 0, what should happen to y? I mean, if input was greater than 0, y was at VDD. If it's less than 0, what should happen? The decision should flip. This should go here and this should go there. That's what you want to happen. But you see here that we have a positive feedback loop that is kind of reinforcing the states and maintaining them at the same level. If you want to change the decision, you will have to pull out a lot of current. In other words, this guy has to be really strong to overcome the positive feedback loop and then start the comparison fresh. Otherwise, the outputs will get stuck at 0 on VDD. Okay? And that's happening because even after we have finished one comparison, we are still holding on to the previous decision. So when we are starting our next comparison, we are starting from the previous result. Right? So if you don't want that to happen, what should you do? You have to reset both these voltages to something. You cannot hold on to the previous result. You have to reset and start fresh. Okay? Probably that is another lesson the comparator is teaching you. No point in holding on to your past for a long time. Every day, have a nice sleep, forget the bad things and start fresh. Okay? So yeah, so now everyone is on the same page that we have to reset these fellows. So what voltage will you reset these to? I mean, okay, he's saying VDD by 2. Okay, let us say, or what, any other choices? I mean, don't say it's difficult to generate voltages. What are the easy voltages I have in the circuit? 0 VDD, he is claiming VCM. Let us say you do 0 or VCM, right? So let us say you are resetting this to 0 or VCM. How will you reset this actually? You want to reset to some voltage. What will I connect here? I have to have a switch here and connect it to an appropriate voltage. And if I reset it to, let us say, 0 or VCM, I have the PMOS transistor. Let us say I'm drawing this guy. Okay. This PMOS transistor, gate is connected to VCM. This is VCM. This is VDD. So this is transistor on. I mean, VCM is roughly equal to VDD by 2. Is the transistor on? It is on. Right? So which means you'll have a direct path from VDD. So which means you are consuming power in the thing unnecessarily, even though you don't want this to be functional. Fine. So that's why resetting to ground or VCM is not a great idea. You try to reset to VDD so that it's completely cut off. And we can do this resetting business nicely because recollect I have one clock period. I am doing the conversion here or comparison here. So here I can go and reset. So when phi c is high, I will basically start the comparison. When phi c is low, the comparator is anyways not used. You are anyways disconnecting this fellow. At that time I can go and reset the nodes to VDD. But at the time if you connect this to ground or VCM, you will be unnecessarily burning current. Fine. So now let's add those also. erase this. This be there. Yeah. So what I have to do is have two switches, and what should be the control for the switch? What should be the controlling signal for the switch? Phi C or Phi C bar? Phi C bar. So I'll implement using what kind of transistor? Switch connecting to VDD. What kind of a switch? PMOS switch. Should be Phi C bar. The clock changes to Phi C in PMOS. Okay. So I'll directly draw this. So this is Phi C. Okay. So now if you reset it, the circuit behaves as usual. X and Y initially start from VDD, and you have the same. So every time you start a comparison, it will start from VDD, and the same thing will happen. No, you just saw it. We cannot reset to 0. You reset to VDD. I mean, in principle, the point is you should forget the previous comparison result. In principle, you can reset to any voltage you want, but we saw that resetting to VDD is the best thing to reduce power. Okay. So this is one nice way to implement a comparator, and it can be used. But there is one minor issue with this, which is the following. So let us say I'll take this example itself. The input is greater than 0. So Y has gone to VDD. So let me actually move to next page. Actually, I only copy this. Hold on. I'm not considering when the comparator is active, so I'll not consider the switches. Okay, I want to reduce clutter in this, so I'll remove the switches because we are considering the phase when the comparator is active. And let us take a case where the differential input was greater than 0, so X went to 0, Y went to VDD. So this is at 0, this is at VDD. Okay. So let's take some numbers. Let us say this is some 1 volt supply. So the common mode is at half the supply, which is 500 millivolts. And let us say this is some 10 millivolts. So this is, similarly this is 500 millivolts minus 10 millivolts, 490 millivolts. The comparator has made the decision. So this fellow is at 0, this is at VDD. So if this is at 0, this transistor is on or off? PMOS gate is grounded, it is on. What can you say about this transistor? Gate is at VDD, it's off. So for now I will remove this guy and just say that gate is at ground, this is also ground. Now we know this transistor is on, which means it is going to draw some current. And look at this NMOS transistor. The gate is source is roughly at 0, right? Gate is connected to 490 millivolt, which is at half the supply rate roughly. Do you think this guy will be on? That will also be on because the gate voltage is close to half the supply voltage. So which means now we have presented a direct path for the current to flow from VDD to ground. Right? So you have something like this. So which means even after you have made the decision, you are actually having a direct path from VDD to ground. You are having a static power consumption. Right? Because remember, I have made the decision here. Okay. So let us say the clock phase is still active. Let's say you have made the decision quick enough. So even after you made the decision, you are unnecessarily consuming power from VDD to ground. Which one? No, this will be at 0. I mean, close enough to VDD, let us say. Very close to VDD, right? This will be in triode region. So this is not a great thing. And again, this will happen for actually small values of differential input. If let us say I take a differential input of say, I don't know, 450 millivolts. So this is 450 millivolts. So this is 950 millivolts. Whereas in the other side, it will be minus 450. It's just 50 millivolts. If you have a large differential input, this will be off, we will not have issues. But if you are dealing with relatively small differential inputs, you will have a static power. So that's something we would like to avoid. And again, think about it. The reason is because we have both the transistors on and these two guys are connected together. That is why we have presented a path from VDD to ground. Fine. Now I want to break this path. After the comparison is made, this is at 0. I don't want to have this direct path, which means should I be connecting the NMOS and PMOS together? I should not be connecting them together. I should put something in between to break it. Okay. So let's see what we can do. Take this here. Sorry? Okay, but the thing is, the point is phi c is like this. Okay, this is phi c. This is phi c equal to 1. The comparison would have been over here itself, but still I will be consuming power here. I cannot know when the comparison is over. I mean, one thing is what he suggested. If you detect that the comparison is over, you can turn it off. But that is slightly bit tricky. So let me actually erase this for now. So one thing is clear, we should not be connecting this like this. So I'll erase it. I'll need to put something in between. Let's say it's an element A and B. And let's take the same case we considered. Vx was 0. This was at VDD. I'll write in a different color. Vx was 0. This was at VDD. So when Vx was 0 is when the PMOS was on. At that point, do you want this element to be on or off? I mean, when this Vx is 0, the PMOS is on. Do you want this to be conducting or it should be not conducting? So if I refer it here, I want this element B to be off when Vx is 0. Fine. Now, when Vx is 0 and Vy is VDD, what do you think A should be? Should it be on or off? Remember, X should be 0. If X has to be 0, do you think A should be on or off? Why not? If it's off, how is this connected to ground? Remember, the only way for X to be pulled to ground is through this. Right? I mean, just because I have written 0 doesn't mean it will be at 0. This is my VDD, this is at ground. If this is at 0, which means I have a path for this. So A should be active. Okay. So A should be on. That is when Vy is at VDD. So now look at this and tell me, I want something to be off when some voltage is 0, on when some voltage is 0. What should I use? It's kind of an NMOS, connect with the gates connected to the appropriate voltage. So I'll try to replace B first. The gate voltage of B should be connected to what? Vx. Okay. So I'll replace B. So I'll replace it with an NMOS. We'll replace it slightly. And the gate is connected to Vx. X and Y are settled or? Correct. That is at the, yeah. No, we cannot detect when it is settled and stuff, right? We'll put the circuit like this and see what happens. Yeah, I mean, we'll see what happens in the voltages, okay? So this is done. Similarly, A has to be replaced by another NMOS. What should the gate of this NMOS be connected to? Dy. So I'll again replace this. Okay. So now the hope is when I add this transistors will kind of shut off the path, direct path from VDD to ground. So you will not have a static power consumption once the comparison is done. That's the idea. So now time to stare at the circuit. Look at this. So I have an NMOS, I have a PMOS, drain of NMOS connected to drain of PMOS, gate of PMOS connected to gate of NMOS. So at this point, you should feel like this. You must have seen this somewhere. This is a classic circuit. And what circuit is this? Everyone has seen CMOS inverter? It's not, if I say inverter, you should not think it's power supply inverter, right? CMOS inverter. So now this is a light bulb moment. So what I can do, I can basically redraw the same thing slightly in a beautiful way. So what I'll do, I'll maybe copy paste this. So what I have is this essentially, I have a CMOS inverter. One CMOS inverter. Similarly on the right side I can highlight that is also another CMOS inverter. Fine. Now look at this. The output of the right side CMOS inverter is connected to the input of the left side CMOS inverter. So output of the right side CMOS inverter connected to the input of the left side CMOS inverter. Similarly, I mean, now we should not take an expert to figure the other connection. Should be obvious. So and then I have the rest of the circuit as before. See, let's say this is V1 and V2. Same thing I have drawn in a slightly more visually appealing manner, that's all. And as usual, I label the output nodes as X and Y. So again, remember, before I start any comparison, what should I do to the outputs? I should reset to VDD. Okay, so I'll have same set of switches as before. So if I draw the full circuit, so clock.phi. So this is called as the StrongARM latch. So yeah, this is StrongARM latch, and if you think this name is something to do with honoring Neil Armstrong, you are absolutely wrong. This has nothing to do with him. In fact, it turns out the designer who came up with this, his name was Kobayashi, was working in Toshiba, but then this design was later used by another company in their microprocessor. That microprocessor's name was StrongARM, so people started calling it StrongARM latch. So probably another life lesson Comparator is teaching you. If you come up with something new, put your name next to it before, so that history books will remember you. Okay? And in practice, we do another modification. Just like how we reset these nodes, we also reset these nodes. Let's say call it P and Q. for similar reasons we do this also. Okay. We'll have another switch here. Fine. Great. So by the way, this is called latch because if you see what I have is a CMOS inverter. The output of the first CMOS inverter goes as the input of the next CMOS inverter, and the output of the second CMOS inverter goes back to the first one. It's like two snakes biting their heads and tails. So people who have taken any digital course should be able to recognize this. What is this? Huh? Yeah, what is it called? Huh? People have taken. I mean, this is called the latch, right? How do you make a flip flop? Huh? You have two latches, one is positive, other is negative. This is basically a latch. So that's why it's called StrongARM latch. And of course, the StrongARM latch is one of the commonly used comparators. But of course, this is not the only one. There is a lot, whole bunch of different variants of this. And in general, these kind of latches are called regenerative latches. Okay. And at the heart of any regenerative latch, you will either find a cross couple pair. So it could be a PMOS cross couple pair like we started with. So we have something like this, or you can have an NMOS cross couple pair, or you can have both of them acting in tandem. That is basically, you put NMOS and PMOS in together, that's the CMOS. So you can have multiple kinds of latches to make a comparator. But at the heart of any regenerative latch, you will find one of these structures. So that is again, to get this regenerative action, the e power plus p by tau, you need the small signal negative impedance, and that is what is being emulated by each of these structures. Cool. So again, now through some line of thought, we came up with the StrongARM latch, but let's actually see if it works, how the node voltages look like, so that we get a full picture. Because every time we cannot trust our intuition. We intuit something, come up with something, but then you verify it's working as we expect. Okay? So first of all, tell me when phi c is 0, what can you say about the node voltages x, y, p and q? All these four are reset, or we say it's pre-charged to VDD. So during this phase, I don't have to do anything. So we know this. So let's just look at what happens when phi c is made equal to 1. Okay. And when phi c is made equal to 1, the PMOS switches are active or not active? They are not active. So I'll basically make them disappear. So let me push it to a side, and this also I know before. Cool. So let me draw this. So let us say this is phi c is 0, phi c is 1. Let me sketch P and Q here. So when phi c is 0, they were at VDD. Okay. Similarly, the outputs X and Y, they were also at VDD. Okay. Yeah, clear? So now remember again, at every node there is a parasitic capacitance. Okay. So now I have enabled the comparator, and let's assume the differential input to be greater than 0, which means V1 is greater than V2. Okay. So now tell me, when phi C is just made active, all these nodes are at VDD. So both X and Y are at VDD. So gate of the PMOS is at VDD. This is also at VDD. Do you think this will be conducting? Gate of the PMOS is VDD, it will not be conducting. Look at the NMOS. Source is pre-charged to VDD. Even the gate is pre-charged to VDD. Will the NMOS be conducting? So initially, these 4 transistors will not be playing any role. So what will be conducting initially? Phi C, yeah, this switch is on. And what else? These guys, right? Because remember, P and Q are charged at VDD. So drain of those NMOS transistors are at VDD. That will be fine. I applied inputs. So obviously I will be drawing currents. And which current will be greater? Okay. So I am drawing only currents from these capacitors now. So initial phase, these guys are not active. Only this fellow is active, right? So I am drawing currents from these nodes. What will happen to P and Q? They will drop. Which will drop faster? So this is P. Now when this is happening, what can you say about the outputs? We just clarified that these 4 transistors are not conducting, which means what can you say about the currents in the transistors? So what can you say about X and Y? Nothing will change. X and Y will be at VDD. Okay. Now P and Q are starting to drop. So what will happen? Source voltage of the NMOS transistors are dropping. So what will happen? No, initially all 4 were off. Now I see that the source voltages are dropping. So what will happen? NMOS will start to turn on. And which of the NMOS will turn on first? P is dropping faster. So this fellow will turn on first. If this starts to turn on, what will happen to, okay, let's see. At this point, let us say P is dropping faster. So let us say at this time instant, this NMOS has started to turn on. If this has started to turn on, what can you say about the current in the transistor? Is it 0 or non-zero? Non-zero. A current is being drawn by this PMOS transistor, and that has to be coming from the node X, because PMOS is still not active. So we are pulling current from Vx. What will happen to Vx? It will drop. And similarly, after some time, this will also turn on. Y will also start to drop. So we'll have this, and first X will start to drop, and after some time Y will also start to drop. Okay. So let me mark things here. So in the first phase, only the NMOS amplifier, differential amplifier NMOS was active. Now in the second phase, all NMOS are active. Okay. All these 4 NMOS transistors are now active. So Vx and Vy are dropping. Now we saw X is dropping faster. If X is dropping faster, gate voltage of this PMOS is dropping faster. What can you say about the current pushed here? The gate of the PMOS is decreasing. So the current in the PMOS transistor will start to increase. So which means we will be pushing in more and more current into that node. Vy will start to increase. So after some time, maybe I have exaggerated, let me slightly make it more realistic. So at this point, let us say the PMOS is starting to turn on. Okay. Remember, initially only this one was on. After P and Q started to drop, these transistors started to turn on. Now after some time both Vx and Vy are starting to drop, which means the PMOS transistor will now start to turn on. Okay. So first this guy will turn on, start to push in current, so which means Vy will start to increase. Okay. So let me say this point, at this point all transistors are on. I will say, and once it has regenerated at this point, once it has regenerated, is there a direct path from VDD to ground? Yeah, I mean in fact we added this fellow for preventing that. So once regeneration is done, everything is off, VDD and ground are shut off. So that's what happens in a StrongARM latch. We have we can say three things happen. First, the amplifying transistors start to conduct, they will draw currents, that will slowly turn on the NMOS of the CMOS inverter, which means the outputs will now start to drop, and once the output starts to drop is when the PMOS transistor will start to turn on, and then you will have the positive feedback happening, and then the regeneration kicks in. You are all set. Okay. So yeah, so it luckily it works as we expected. So yeah, a couple of minor points in this, and then we'll wrap today. Sorry, can you repeat the question?
It stays there in the StrongARM. There are three phases: amplification, regeneration, and the reset phase. Okay.
I mean, we have only two phases. One phase where we reset everything to VDD. Other phase is the comparison or regeneration phase. That's all. I mean, in the regeneration phase, you can say three things are happening distinctly. That's all. Cool. So hopefully StrongARM latch is clear. It's okay. Let's see if I can copy paste it. Did I have this? Great. Oh yeah, that's a good question. Where do you think what will happen to these two?
Eventually, DNQ will stop, right? I mean, it will stop the power.
I mean, you find that you'll draw this and both of them will kind of go to zero. Both of them will drop. I mean, you are still drawing current, so both of them will drop. I mean, why do you want to make it like an amplifier? Yeah, they are amplifier, right? In fact, that's how we started, right? We started with a common source. This is an amplifying device. These two are common source amplifiers, and what we did was to increase the gain and regeneration, we put a small signal negative resistance. In fact, this is amplifying because if you see, initially, if I look at the nodes P and Q, initially they were equal, and as time progresses, the difference between them keeps increasing, right? So this is actually an amplifier. We will come to this later. This in switch capacitor circuits we use this kind of amplification actually. Now again, if the X and Y, yeah. Okay, cool. So couple of minor points. First point. So let us say now I am interested to find the power consumption here. Power consumption is what is the current I am drawing from the supply VDD. That's all. So maybe okay, I'll draw it here. Let's say this is the clock phi c. Now when phi c is 0, is there a, I mean, are we drawing any current from the supply? When phi c is 0, what's happening? This node is VDD, this is at VDD. So everything is at VDD, no current flows. When phi c is 0, this phase 0 current. If I plot the, if let us say I call this as the current I supply. I mean, but let us say it is charged, right? I mean, okay, we'll come to that. But let us say we are looking here, wherein voltages are settled to VDD. Fine. So at this point, let us say it is 0. Now I am making phi C active at this point. So when will there be a current drawn from the supply? Remember, when the phi C, when comparator is activated, we saw 3 distinct operations. First is when this was active. When this was active, were we drawing a current from the supply? No. In fact, when this was active, this is not. We are only pulling out currents here. No. When this turned on, did we draw current? And when will it draw current? Only when the PMOS turns on. And remember, that turns on for a short while. Regeneration happens quickly, and once regeneration is completed, there is no path from VDD to ground. Okay. So once phi C is activated, for a short while you will draw some current. That's all. Okay. Yeah, we'll draw a small current like this. Yeah. I mean, we'll come to that. Yeah, we'll come to that. Yeah. So now, let us say I am making phi C go to low. At that instant, what do you think will happen? When phi C is just made low, remember, I have these switches. This can be any node X, Y, P or Q. I have a switch, and at each of these nodes there is a parasitic capacitor. I am trying to precharge this to VDD. When I close the switch, what will happen to the current? Huh? I mean, if it's an ideal switch, what will be the current? It's an impulse current. No, CVDD is not current. What is CVDD? It's a charge. Okay, so it's an impulsive current. With real switches, it won't be impulsive. You will have some spiky current like this. So now tell me, at what all time points I will be consuming power here? Only rising edge, or only at the clock edges is when a current is even drawn from the supply. So this is what we call as a dynamic circuit. That is only when the clock makes a transition, some current might be drawn from the supply, or current will be drawn from the supply. If the clock is not changing, no power. So if you don't want to use a comparator, you can disable the clock, and it draws no power. So, and that's what we call as zero static power consumption. And again, people who have taken digital circuit will know that's why you use CMOS logic, because it has zero static power consumption. Cool. That is one advantage of this StrongARM latch. So there is no static power consumption; it's purely dynamic. And if you see, I just need one clock phi C. I don't need phi C bar, and all that business. So one last point, and then we'll wrap. So let's say now I have the StrongARM latch. These are the outputs. And let's say if I draw the clock phase here, this is when phi C is made high. Hold on. Yeah. So this is when phi C is 0. This is when phi C is 1. So when the clock phi C is 0, what can you say about the outputs? Huh? When phi C was 0, what were we doing to the outputs? We were precharging the output nodes to VDD. Okay. So at this point, the output is not available. So only after you activate the comparator, after a short while is when the compared output is ready. Right? At this point is when you can get a valid logic 0 or logic 1. Fine. Now remember, this is supposed to be converting analog to digital. It has made a comparison, and it's giving whether it's logic 0 or logic 1. So following this, you might have some digital circuit or some DSP running on this, and those circuits will think that they will be expecting the logic levels to be stable for one whole clock period, right? So which means I cannot directly go and interface this. So after the output is available, I should do something so that the output is ready for one whole clock period. What do you think I can put here? No capacitor. I mean, your thinking process is correct, the answer is wrong. You have to store the output somewhere. It's a digital data. What do you use for storing a digital data? Register. I mean, latch, flip-flop or a latch. So, I mean, latch is enough because flip-flop is basically two latches. So, in principle, we put a latch, and most common is an SR latch. This will make sure that the output is held for the entire clock period. So, even when the output is getting reset here, you are supposed to hold whatever result was there before. I mean, yeah, capacitor is again, the idea is correct. You have to store it. It's a digital circuit. Better thing to store it is, and I mean, this is the output of StrongARM latch, let us say. So, you guys remember how an SR latch is made? Yeah, cross coupled NAND or NOR. So we can use a cross coupled NAND here. So once again, you see, even in this SR latch, you have this cross coupling business. Okay. So let us say this is the output of the StrongARM latch that you are directly feeding. Let's see if it's serving our functionality. Let us say after the comparison, the output is 0, 1 like this. Input to the NAND gate is 0. What will be the output? NAND gate 1. So this will be 1. So this is 1. This is 1. This will be 0. Of course, we have flipped the decision, so we can put a CMOS inverter and kind of get it correct. But the important thing is, even when I am resetting this, I should hold this, right? So let us say I reset the outputs, I reset both of them to 1. Now let's see what happens. So this has become 1, okay, this is still 0, this will be, I mean, this has become 1, whereas this is still 0, so this will still be at 1, nothing will change. This is 1, this is also 1. So this way we can make sure that the output is ready for one whole clock period. Now, I mean, you can also make an SR latch with NOR gate, but when you use a NOR gate, if it's 1 and 1, you will have an issue. So you have to invert it and use. Okay, so if you are using a NOR based latch, SR latch, you invert the outputs and then kind of do this. Because for a NAND SR latch, 1 and 1 means its whole state. For a NOR SR latch, only if it's 0 and 0, it is a whole state. So you have to invert the StrongARM latch outputs here. Yeah. Let's stop here. We'll continue.